if I hold this mass up and I drop it, what's going to happen?
It's going to fall.
It's going to fall towards this hand. But do you see anything connecting this hand to this hand? So if I put my hand here and it moves towards it, oh, that's magic. If I put my hand here and it moves towards it, oh, that's just gravity. Okay? So if you look at the definition of magic being you making something move without a noticeable outside force acts upon it, gravity is magic. Okay? Just saying. Physics is built on magic. I make my living teaching you mathematical magic, but it's okay. It's true. Like look at the whole dark matter and dark energy thing. Yeah, I am basing my career on a universe that we don't know where 80% of the mass is. Sorry. It'd be like me guys teaching you history, and it's like we only know about 20% of the history of the world. The other 80% we're a little fuzzy on. We don't know what happened. Roman Empire, maybe, we don't know. Okay. So, well, it's a true story, Lauren. I mean, English, Shakespeare, whatever. Okay. All right. So let's talk about gravity. All right. So we're going to work with two broad types of problems on gravity. One is when we just drop something, and then the other one is when we like throw something up in the air and hope it comes back down. Okay? So we're going to work with the dropped ones first. So we're going to drop something, and we'll deal with it just this side first. So if we drop it, and this isn't, let me explain what this is. This isn't like a gang, a physics gang. We're the members of the VYOs. Okay? This just means my initial vertical velocity. Okay? That's all we're saying. So if you take something and you hold it up in the air, I need something that bounces. I should have had tennis balls. Gannon, can you throw me one of those tennis balls? Please? Well done. Thank you. Okay. So here I have yonder tennis ball. Okay, it's a Wilson 3 if you want to play along. So I hold this up and I'm going to drop it. So there's three options that I could do. I could just drop it. I could throw it up like that and have it fall, or I could throw it down like that. So initially we're just going to go doink, then we're just going to drop it. So the other thing that's going to happen is that in any situation, anything going down, whether it's displacement, velocity, acceleration, anything going down is going to be a negative number. Okay? So that way we're consistent. And our acceleration, and this is going to be true for both of these, is negative 9.80 meters per second squared. Typically we just say this is negative 9.8. Technically there's a 0 there, so that technically gives us 3 significant digits. This number actually changes depending upon where you are on the Earth, but on average, this is what we're going to use. Now, amongst my list of pet peeves, don't ever say, oh, gravity is negative 9.8. Oh, for the love of God, stop. Okay? This is not gravity. You can say, oh, the acceleration due to gravity is negative 9.8 meters per second squared. Okay? And I know I'm just being picky, but it's just wrong. I mean, it's just like saying, oh, there's cool freshmen. No, that's wrong. Okay, there aren't any. I take that back. I had Adeline when she was a freshman.
Yeah, I was about to say something.
Yeah, I had Adeline in an encore when she was a freshman, and she was cool.
Yes.
Yeah, me too.
Yeah, she was cool.
Yeah.
Oh.
You were this gangly freshman. Okay.
At least I stuck around.
Yeah.
I'm sorry.
And Bodie left like the first day.
Were you in there the first day?
Like the first week.
Okay, I've slept a lot.
This is
since
like
then.
a
And
reunion.
so,
I feel left out.
So much anger.
I know, there's anger.
There's betrayal.
encore freshman drama. Here we
It's
go.
like passive aggression more than there's anger.
Maybe we should just sit around in a circle and sing Kumbaya. I don't know. Okay. So what we're going to do is we're going to look at this. So we're going to work, if we can figure out one problem, we can figure out a whole bunch of things. So I'm going to hold this ball up in the air to a height of 2 meters, and I'm going to drop it. Okay? So here's the ball, 2 meters above the ground, and I'm going to drop it. So I'm going to figure out how long it's going to take for it to fall. I want to figure out how fast it's going at the point of impact. Okay? And then I want to figure out how fast it's going after 0.40 seconds into the fall. Okay? So let's start with this. As soon as I drop it, and this goes into this broader idea called Jedi Stoffel Law, which we'll spend a lot more time talking about.
What? That sounds good.
It is. Jedi Stoffel Law stands for stop the force and watch. Okay? All right? So Jedi Stoffel Law, stop the force and watch. So if I stop applying the force to the tennis ball and I watch what happens, it begins to accelerate. Mother Nature is a lazy prima donna. Mother Nature doesn't like things that accelerate. So if I drop that ball and it begins to accelerate, that means there has to be an external force acting on that ball. If there wasn't, the ball would just hover right there and you would all go, oh, witchcraft, okay? But because there's this magic gravitational field, right, I let go of it, it begins to pull it down. So, there's a whole bunch of things that we do know. We know the initial velocity is going to be 0. Even though I don't explicitly tell you this, I know the initial velocity is going to be 0. I know how far it's going to fall, and I know my acceleration due to gravity. So I know those 3 things. So let's, if you look at V, V naught, dat. So on any gravity problem, you're always going to know the acceleration. So this is going to be negative 9.80 meters per second squared. I know how far it falls. Now, I'm going to leave a gap. Okay? And I'll fill this in. And I'm going to put the 2 meters. Okay? You'll see later on why that's going to be important. Then, I've got my initial velocity, which is 0 meters per second. Okay, so we're going to tackle time first. Now, there's a couple of ways you can do your position, and I don't care how you do this. Typically, what you're going to do is that you're going to define the point of release as being 0, and then your final position when it hits the ground is going to be a negative value, which would be like negative 2. So if I make this position up here, my P naught, be 0 meters, my final position is going to be negative 2 meters. Later on, you'll see why that's so vitally important. Now, the other option is that you go, Bergkamp, I want to make the ground 0. Fine. We'll make the ground 0. This is another option. The other option is that you make the ground be 0, and then you make your initial position be 2 meters. Now, here's what's important. In these equations, I need displacement, not distance. I need displacement. So if you know position initial and position final, how do you calculate displacement? What minus what? Position final minus? Now, so if we go with this one, my final position is negative 2, my initial position is?
0.
So what's my displacement?
Negative 2.
Negative 2 meters. Now, if I go with this system, what's my final position?
0.
What's my initial position?
2.
What's my displacement?
2. Negative 2.
Negative 2, because it's final minus initial. So no matter how I set up this system, I'm going to have a displacement that's negative 2. And later on you'll see why that's so vitally important. Okay? Now, let's tackle time. I got distance equals 1/2 AT squared plus V naught time. You guys have that as X. Okay? So here's the deal. I'm going to drop this thing. So what's my initial velocity? 0. So this is cool. So this whole part of the equation goes away. I don't have to worry about that. That's gonzers. Okay? Now, if I throw it up in the air, I can't do that.
Yeah, because of how it's
If I throw it down, I can't do that. But if I drop it, or if a car starts from rest or something like that, then you're in it all day long by doing that, okay? So this is going to go away. Do you know how far it falls?
Yes.
You know your acceleration.
Yes.
What's the only thing you don't know?
Time.
Time. Get in the habit of solving these equations. So if I solve this equation for time, what does it look like? Josh, solve that equation for time. And I hate fractions.
The square root of 2d divided by a.
Beautiful. Okay? So multiply by 2, divide by 8. Now, this isn't like a big dog equation. It's more of a pup, but it's a very important pup. You're going to use this a lot. Okay? This is one of the most handy-dandy little equations you will ever have, especially in dealing with gravity where things are falling. Okay? It's a great little equation. Now, I'm going to show you, what I'm going to do is wrong. Okay? Do not do what I'm about to do. Okay? Because here's what I'm going to do. I'm going to go, okay, great. I know I got 2 times 2 meters, right? Oh, that's gravity. I got negative 9.8 meters per second squared. Okay? Now, why mathematically is this going to be a train wreck?
You can't have a negative in a row.
Oh, you can.
Well, it's going to be imaginary.
Yeah, you can have imaginary
Yeah.
time. Okay? Which is
That's
cool,
magic.
don't get me wrong, all right? Imaginary time. So at this point, you're in a quandary. Okay? One quandary is that you go, there we go, we're good. It's all good now. We just make that positive. But here's the problem. Now you just can't do this because now you've completely changed the entire set of parameters on the problem. Okay? You have in your screw. You have to stay with a consistent set of parameters on how you work this problem. So don't do that. That's bad. Poor form. But this is where you work the problem holistically. Since this is displacement, what's the value of this? That's negative 2 meters. Oh, that's kind of punchy. Now what happens?
It's a negative over a negative and yet positive.
Yes, now I've got 2 negatives underneath the radical. Now I have positives underneath the radical. Now I'm good. Now, in reality, here's the story. Am I going to know if you made that positive or negative? Yes, I will, because I'm going to look at this, okay? This is one of the things I'm going to look for. And I don't do it to be a jerk. I do it to force you to think through the problem. Again, you all are used to plugging numbers into a calculator and trying to get an answer and write that down. It's not what physics is about. You have to look at a big picture. So, this is the other thing that you're going to do wrong. You're going to do all of this, and then you're going to forget to take the square root. Okay? Trust me on this one. Seen it done 100 times. Give me this answer. Let's just go with 2 significant digits, because I just got 2.0 meters. So give me this with 2 significant digits. 0 point something.
0.64.
0.64 seconds. Okay? That's nice. That's nice. Because basically, I'm going to drop this thing. I want to go 1 missile. Okay? So 0.64 is equivalent to 1 missile. Okay? So how far we're getting on this one. Okay. So I got this. Now, what is my velocity time graph going to look like? Where's my velocity time graph going to start?
0.
0, right? Is it going to slope up or is it going to slope down?
Slope down,
Why?
because it's a negative
We're
acceleration.
defining down as being negative when we have negative acceleration, right? So this is going to slope down like this, okay? Now we know we're at 0.64 seconds. So this is going to be out here at 0.64 seconds. And the slope of this line is going to be negative 9.8 meters per second squared. Okay, here's the slope of my line, negative 9.8. This is why this can't slope up. This has to slope down. Now, if, and this is a huge if, if this time is right, could I use that time to calculate the velocity when it lands?
Yes.
Yes, because if it fell for 1 second, okay, if this fell for exactly 1 second, what would my velocity at impact be? Negative 9.8 meters per second, because this is what this means. This is your rate of change in your velocity. So if something falls for exactly 1 second, it's going to be going negative 9.8 meters per second at the point of impact. But I don't fall for a second, do I? So my velocity at impact has to be less than negative 9.8. Now, so one option, and I don't recommend this option, okay, but I'm going to do it. I wouldn't work the problem this way, but this is what you could do. You could go, oh, we want to find the final velocity. So you could go v equals v naught plus at. It's a slope-intercept form. Do you know the initial velocity?
0.
0. Do you know your acceleration?
Yes.
Yes. Do you know how long it fell?
Yeah.
0.64 seconds. So I could use this to find that final velocity. But what's the problem? What if this answer is wrong?
Yeah.
If that time is wrong, guess what?
Your final velocity.
Your final velocity is going to be wrong. Okay? Now, we're going to do it this way just to get an answer. So, Josh, take 0.64 times negative 9.8 meters per second squared.
Negative 6.27.
Negative 6 point what?
27.
Okay? Meters per second. So that's going to be the velocity at impact. Don't tell me, oh, it's going to be 0 when it lands. No. This is how fast it's going at the point of impact. Okay? So, this is cool. You can take negative 9.8, there's your acceleration, multiply that by the time, you can get this velocity. Problem is if this time is wrong, this answer is wrong. So is there a way to find the final velocity without using time?
Based on the way you've been talking about it.
Yes.
Maybe that equation?
B squared equals
Yeah.
initial velocity.
Do you know your initial velocity?
Yes.
Do you know your acceleration?
Yes.
Do you know how far it goes?
Yep.
Yeah? Oh, that's kind of cool. So, I'm going to drop this out. I'm going to do this wrong. Okay? Do not do what I'm about to do. So I've got to take the square root of both sides. So I'm going to take 2 times negative 9.8 meters per second squared times 2 meters. Why, again, why is this going to be a train wreck?
Imaginary velocity.
You're going to have an imaginary velocity, which is great if you get pulled over by the cops. You know how fast you're going? I got kind of an imaginary velocity that I think I'm going at, which will get me out of the speeding ticket. I don't recommend you say that. They're probably not going to find that at all
Oh,
fun.
yeah.
Just say, no, sir, but thank you very much. All right. So, what do I have to do, though? If you work it consistently, then you're going to have that negative 2 meters. Then you have 2 negatives underneath the radical. Now, this is where your calculator will lie to you. Okay? Your calculator will lie to you. You're going, oh no, Mr. Burkett, my calculator would never lie to me. It's my best friend. Yes, it will. What's the square root of 4? 2, or, guess what? You have to choose the negative root for this. Okay? The disadvantage of this process is that your calculator won't give you the negative root. This requires a little bit more thought, but you're going off of numbers that you have. So if you do this, if somebody take 4 times 9.8 and the square root of that, you should get like around 6.27.
6.26.
Yeah. But you're just going to choose the negative root and go, oh, that's negative 6.26 meters per second. Now, here's the other thing, how this plays out. Notice on my displacement, this area underneath your velocity time graph gives you your displacement. If you were to just calculate this area right here, you're going to have a positive time multiplied by a negative velocity. You're going to get a negative displacement. Out of curiosity, Josh, take negative 6.27 times 0.64 and then take half of that.
-2.
Yeah. So why is this area negative 2 meters?
Yeah, because
That's how far it fell. Okay? So that's how you can kind of always work backwards and figure this out. Now, if I ask you to draw velocity vectors on a problem like this, it's pretty simple. All you'd have to do if I said, hey, draw some motion diagrams. You just go, oh, here's V1, there's V2, there's my negative acceleration. That's all you'd have to draw. Okay, that's it. Don't make it complicated. All right? Cool with this one. Okay, stand up, take a very, very quick stretch, and then we'll keep going on throwing it all up in the air.